Welcome to our explainer on one-dimensional kinematics. So our main goal today is pretty straightforward, but honestly, it's incredibly powerful. We're going to help you leap over the three biggest conceptual hurdles in this subject. If you've been grinding through those foundational concepts of motion, well, you are absolutely in the right place. Look, anyone who has ever studied physics knows that early sense of frustration, right? You're handed this massive pile of equations, and it is so tempting to just start plugging in numbers and hoping for the best. But true physics, it isn't just math, and it's definitely not about plug-in-chug memorization. It's really the art of translating the messy, real physical world into clean, logical models. So today, we're moving way beyond just hunting for the right formula. We're going to build some true physical intuition. To do that, here's our roadmap. We're going to conquer three distinct boss battles, or milestones, together. First up, the catch-up challenge. Second, vertical freefall. And finally, graphical mastery. Let's get right into it. Milestone 1, the catch-up challenge. Okay, let's dive into this. This first milestone totally shifts our focus. We're moving from analyzing just a single, isolated object floating in a vacuum to orchestrating a fully interacting system. Picture this. A motorist traveling at a constant 15 meters per second just blows past a stopped police officer at a school crossing. The exact moment that motorist passes the sign, the officer immediately starts in pursuit. So you're no longer just calculating where one car goes, you're literally modeling a chase. To actually solve this, we first got to recognize that these two vehicles are living in completely different physical realities. Our motorist is just cruising at a constant speed. That means their acceleration is zero, so their position equation is super simple, just velocity times time. But the police officer is starting from a dead stop and speeding up with a constant acceleration of 3.0 meters per second squared. That means their position relies on 1/2 acceleration times time squared. Setting up the proper logical framework means we have to create these two totally separate equations of motion. And this brilliantly illustrates the ultimate light bulb moment for this whole milestone. When you look at the position time graph for both of these vehicles, you'll see the motorist's path as a straight diagonal line, while the officer's path swoops upwards in a parabola. So how do we mathematically translate the everyday English phrase, the officer catches up to the motorist? Well, it's the exact moment those position time graphs cross. At that specific split second, their positions are perfectly equal. By simply setting their position equations equal to one another, we unlock the algebra to actually solve for time. The math cleanly shows that exactly 10 seconds after passing the sign, the officer and the motorist are at the exact same position, which is roughly 150 meters down the road. You've essentially taken two distinct models of reality, mashed them together, and predicted the exact moment they intersect. How cool is that? Milestone 2, vertical freefall. All right, this next milestone is the absolute ultimate test of your understanding of directionality and the relentless, unstoppable nature of gravity. First things first, we got to establish our sign conventions, so let's define up as positive. Now, imagine you're standing on the edge of a roof railing and you throw a ball straight up into the air with an initial positive velocity of 15.0 meters per second. The ball leaves your hand, climbs higher and higher, slowing down as it fights against gravity until it reaches its absolute highest peak, right before falling all the way back down past you. I want to pause the narrative right here. Let's literally freeze the ball at the very top of its path. This brings us to the single most common trap students fall into. At this exact peak, when the ball is at its maximum height, what is its acceleration? Be honest, if your instinct was to say 0, you aren't alone. But you'd be wrong. The shocking truth here is that the acceleration is not 0. No way. It is exactly negative 9.80 meters per second squared. See, gravity does not care that the ball has momentarily stopped to turn around. That downward gravity vector is a constant, looming presence from the literal second the ball leaves your hand until it smacks into the ground. I absolutely love how our source material addresses this. It throws a giant caution sign right at this free fall misconception. It points out that, hey, if the acceleration suddenly became 0 at the top, the ball would just magically hang there, suspended in midair, kind of like a cartoon character that just realized it ran off a cliff, right? Acceleration is the rate of change of velocity, and at that peak, the velocity is absolutely changing. It's shifting right from positive to negative. Now, what's really interesting about this is how we can use that momentarily 0 velocity to our advantage. Even though gravity never takes a break, knowing that the vertical velocity hits zero exactly at the peak gives us the mathematical key to calculate the maximum height. By plugging in a final velocity of zero, the kinematics equation cleanly outputs a peak height of 11.5 meters. And side note, if we later wanted to calculate the exact time it hits the ground way down below, we'd use the quadratic formula. That teaches us to critically evaluate our math and just toss out any negative, non-physical time results. Milestone 3, Graphical Mastery. Okay, let's switch gears and learn how to translate those complex algebraic formulas into pure visual geometry. So many learners struggle to bridge the gap between a written equation and a visual plot. But think of this table as your definitive cheat sheet. It shows you exactly how to extract entirely different physical meanings from a single plot of ink on a page. Depending on what type of graph you're looking at, checking the slope gives you one rate, while looking at the area under the curve gives you an accumulated total. For instance, if we look at a position time graph, it's not always going to be a neat straight line. Often it's curved. So to figure out the instantaneous velocity at any exact moment, you have to imagine riding a tangent line right along the curve. This is basically calculus light in action. Visually, the steepness or the slope of that tangent line at any given point perfectly equals the instantaneous velocity. Conversely, if we look at an acceleration time graph, the slope isn't what we're after at all. Here, we look at the visceral action of shading the area underneath the plotted line. That colored rectangular space isn't just empty geometry. It reveals hidden physical properties. The total accumulated space bounded by that curve directly equals the object's total change in velocity over that specific time frame. And similarly, the area under a velocity time graph equals the total displacement. So, when you're faced with a really complex motion graph, like tracking our police officer from earlier through a period of constant velocity, then positive acceleration, and finally a rapid deceleration, please don't get overwhelmed. Just do a segmented analysis. Step 1, break the trip into distinct phases. Step 2, calculate slopes to find the instantaneous rates for each segment. And step 3, calculate the geometric area of each segment, your triangles and rectangles, to find the overall change. Breaking it down like this makes extracting graphical data so intuitive and honestly incredibly satisfying. By mastering these 3 milestones, systems of interacting objects, the unyielding directionality of freefall, and graphical data extraction, you've built yourself a rock-solid foundation. Because ultimately, whether you're dealing with algebraic equations, positive and negative signs, or geometric areas on a graph, these are all just storytelling devices. You are doing the magical work of mapping reality. And that leads me to leave you with this final thought. If you can leverage a few simple lines on a graph or a basic quadratic equation to confidently predict the exact future position of 2 speeding vehicles or a falling object, what else in the physical universe do you think you can calculate next? Keep that curiosity alive, and we'll see you in the next explainer.